And we are live. Hey, how's everybody doing tonight? It is Monday, April 27th. Had to look at my calendar there real quick. Welcome to AE Live tonight. We've got a special AE Live tonight. I want to bring on with us Cadet Master Sergeant, Senior Master Sergeant, Cadet Iris Kenyon. And let's see. Uh-oh, where are you? Uh-oh. Hang on. Technical difficulties. We are going to get this fixed on the fly. Let's see here. Let's see. We're going to figure this out. What's going on? Oh, there you are. Okay, you're on.
Hello.
How are you doing tonight?
I'm great. How are you?
I'm doing fantastic. I hope you're having a good night. What we're going to do tonight is a little different. We are going to go ahead and we are going to do our normal thing. We are going to do some housekeeping. We are then going to move to some news. And then Cadet Master Sergeant, Senior Master Sergeant, is going to do our lesson tonight. So really excited. I will say that my internet connection is really horrible. So right now it seems like we are doing okay. But now not only am I trying to stream to YouTube, I also have a Skype conversation going. So if we buffer out and get a little slow, please just kind of stay with us as we try to figure it out. All right. So with that, we are going to go to our housekeeping. So let me get that up and running. And let's see here. We'll be right back with you, Iris. I'm going to mute you. Okay, you're muted. All right, let me bring this up. All right. So first thing for housekeeping, I found some more graphics to put on. So Aerospace Dimensions 2, Module 2, Chapter 2, Airports is now online. If you were with us last week for our AE Live, a lot of that is going to be the similar information, but now we are actually going to include everything directly from the actual Aerospace Dimensions book. So feel free, if you're working on Module 2, go ahead and check that out. I do plan on releasing Chapter 1, so we're actually going to go backwards. I plan on releasing Chapter 1 in 2 weeks, so not this Friday, but next Friday. Next Monday for AE Live, we will be discussing the Saturn V. I got a really great book on the Saturn V. I also did a live build of the Lego for the Saturn V, and so we'll be doing a high-speed run-through for that. And as always, the normal YouTube stuff. Please go ahead and subscribe and like and share. That helps the YouTube algorithm figure out where we are, and other people from CAP, it'll be easier to find us. And if you subscribe and if you hit that little bell icon, since a lot of our stuff that we do goes live, it will actually let you know. You'll get an alert. Usually a couple of hours before we go live, I'll actually schedule the live lessons and you'll get an alert. I don't always do these at Monday at 7 o'clock. A lot of times I will add additional lessons throughout the week. So feel free to hit that bell icon, and then before I go live, it will let you know. All right, with that, let's go to the news. All right. I had to warn everybody, there's a big asteroid coming, and it's getting really close to the Earth. Now, luckily for us, it's not going to get that close to the Earth. But if you look at this graphic here, it's going to get about 16 times the distance between the Earth to the Moon. And so in relative space terms, that's like razor thin. It's flying right by us. But all the scientists have said, don't worry about it. There's no chance it's going to hit us. So I will be sleeping soundly that night, not worrying about it. So this is going to happen on Wednesday morning, on April 29th. The asteroid is called 1998 OR2. My assumption is that meant that it was observed in 1998, I'm assuming. And so the moon orbits the Earth at 239,000 miles, shows you how far away the moon is. And this is going to be about just a little bit under 4 million miles. So again, it's kind of neat. We'll get a chance to maybe see it up in space if you got a good telescope, but it shouldn't have any problems with the Earth. All right, so the next one. This one's actually exciting. We talk a lot about SpaceX on this on Aerospace Live, and there's reasons for it. They're doing a lot of really great stuff. And so serial number 4, SpaceX serial number 4, SN4. This is their new Starship prototype. This is the 4th one. It actually passed a really significant test this week. It actually had what's called a cryo pressure test. So this is the pressurization of all the cryo tanks. This is one of the things that they've been having problems with. It's been causing the the models actually collapse in on themselves. And so they actually had a successful test, which is great. Believe it or not, this thing that looks like an oversized, wheat or corn bin from a farm, this exact one might actually get some rockets on the bottom of it, put a cone on the top. This one might actually fly. It won't probably go into space, but they're probably going to do a test flight. So this was great. So nice to see they're one step closer to getting this working. So one step closer to getting this thing to the moon and then on the way to Mars. Okay. All right. This next one I thought was pretty fascinating. This actually comes from CNN. A lot of our news articles come from space.com. So if you don't know or haven't been to space.com, feel free to go visit space.com. This one actually came from CNN. So if you look at the left-hand logo, that's what most people call the worm logo. You'll see it if you looked on Saturn V. If you look at the old spacecraft, you will see the worm logo. Pretty much everything since the Nixon administration has gone to what we call the meatball logo. Some people actually call it the Nike swish. It's kind of got that look to it. The reason that the left-hand logo, the worm logo, they've been battling each other. The worm logo was popular, and then it became unpopular, and then the meatball logo came in. And the worm logo really is now, it's coming back to SpaceX, and which I think is super interesting. So the meatball logo is the official logo for NASA. NASA has not gone back to the worm logo, but for SpaceX, they are allowing SpaceX to use the worm logo. Now, why is that interesting? It's interesting because all of the spacecraft that went to, outside of low Earth orbit and went to the moon, they all used the worm logo. And so, my opinion, they are making a statement. They are making a statement by using that worm logo on the SpaceX rockets. That is their goal is to get out of the Earth and go to other places, go to the moon, go to Mars, and the meatball logo is more planetary in its shape and its idea. So it's more idealized towards the Earth. It's more idealized towards space around the Earth. So I think it's interesting. And then I think it's interesting is that so far, from what I've read, SpaceX is the only rocket company that NASA's allowing them to use the worm logo on. ULA, United Launch Alliance, Boeing, they haven't been told, to my knowledge, that they can use the NASA worm logo that was used for the Apollo missions. So I think that's an interesting little dynamic. Does that really mean anything? Maybe not. If ULA asked NASA to use the worm logo, would they allow them? Probably. The other thing that's interesting too is, so the question then is, what is the official logo? Well, the official logo is the meatball logo. But what's interesting is if you go to NASA headquarters, the logo that's on NASA's headquarters, it's the other way. It's the worm logo. And why didn't they change it? Because it's actually carved in granite. So you're always going to have the NASA logo. All right. So with that, we have our presentation. So I am going to unmute you. All right, we can all hear you now, and we are going to say a little bit goodbye to me, and we're going to say hi. There you are. And take it away.
All right, good evening, everyone. I am Cadet Senior Master Sergeant Iris Kinnan, for those of you who don't know me. And today I'm going to be doing a little presentation about engines, which is the topic that you all voted on the last time I did a presentation. So I hope you're all tuning in, taking notes. I can't see you right now, so it's kind of on the honor system. But this is a really important topic for a number of reasons. First of all, engines are obviously very important to aircraft, and if you do O-rides with Civil Air Patrol, or if you move on into an aviation-focused career, you're going to be learning a lot about engines, and you're going to have to know how they work, how to use them, and maybe how to fix them in a pinch. Not only that, even if you quit Civil Air Patrol tomorrow, never board another plane in your life, don't care at all about aerospace, you're still going to need to know a little something about engines if you ever plan on driving a car, using a lawnmower or a chainsaw. Just about anything that needs power in this world is powered by engines. All right. Do you have my slideshow? All right, perfect. So an engine is any machine with moving parts that converts power into motion. And power is basically defined as the amount of energy generated by something per unit of time. So essentially what an engine is doing is it's taking energy and turning it into movement, which, because movement is just kinetic energy, it's taking one kind of energy and turning it into a different kind of energy. And the type of engines we'll be talking about today are converting chemical energy into kinetic energy. Chemical energy is the energy that's stored in the bonds of chemical compounds that when you break them down, for example, by burning them, it releases that energy in the form of heat, light, or in this case, it expands, and we can use that to create kinetic energy using an engine. And they're used to power everything from lawnmowers to airplanes. Anything you can think of is powered by engines, so it's very important to learn about this. I will not be going very in depth and covering all the parts of an engine today. This is a very basic overview. I'm essentially going to be talking about cylinders, the processes that happen inside the cylinder that allow the engine to generate power on a very basic level, and different ways that those cylinders can be configured to achieve different goals with your vehicle. All right, next slide. Okay, so the type of engines that we're going to be discussing today are four-stroke piston engines. There are other kinds of engines like two-stroke piston engines or jet engines that we aren't going to be covering today, mostly for time constraints or because it's very complicated. So four-stroke piston engines are found in cars and aircraft. And basically what happens in a four-stroke piston engine is that fuel, so your gasoline, your avgas, whatever it is that you're using to fuel your engine, is ignited or lit on fire to make a small controlled explosion. And that explosion then pushes a piston downwards. The piston turns a crankshaft, which is basically just a long piece of metal, and then that rotational motion of the crankshaft is used to move the vehicle forwards by spinning a propeller or wheels, and that is what makes the airplane go. And the speed at which the crankshaft is measured is in RPM, or revolutions per minute, and that would be the number of times that your crankshaft turns around 360 degrees in 1 minute. And you can see that from your cockpit on a little dial there, and you can see that in your car, and that's just something important to note. That's what it means. All right, next slide. So now I'm going to talk about the basic parts of a four-stroke engine cylinder. First up, we have the intake valve, which you can see on that diagram there. It looks very complicated, but it's going to be that valve right on the left-hand side with the kind of blue or silver tube leading up to it. And this valve, when it moves up, is going to allow the fuel-air mixture to enter the cylinder. Now, the fuel-air mixture is essentially just your fuel, your gasoline, your avgas, your diesel, whatever, that's basically been vaporized and evaporated and is mixed in with the air as a gas. And that process is completed by something called a carburetor, which has just about a million things that can go wrong with it that I'm not going to get into. But that's the fuel-air mixture enters through the intake valve. Next, we have the piston. This is the main feature of the piston engine, as you can tell by the name. Yes, I can see that Lieutenant Roberts is pointing at it right now. Basically, the piston, it moves up and down. It compresses the fuel-air mixture, and it turns the crankshaft, which is this part right at the bottom here. You can see the white circle, and that's the crankshaft, and you're kind of looking at it from the front end, and it would extend like into the screen and out of the screen. So that piston, when it turns, is going to turn the crankshaft through that linkage that you can see there. Next is the combustion chamber. The combustion chamber is the area where combustion occurs, and it's just that empty space right in between the cylinder, the wall, or the cylinder walls, the piston, the valves, the spark plug. That empty space right there is where all the action happens. right on top of the combustion chamber, we have the spark plug. And this is just a little electrical device that creates a spark. And that spark is what sets off the fuel-air mixture and starts our combustion process in order to push the piston down. Next up on valves, we have the exhaust valve, which is the exact same thing as the intake valve, except on the other side. And rather than letting fuel-air mixture in at the start of the process, it allows the burnt fuel to escape and go out through the exhaust system, so that we don't have all that exhaust, taking up space in the cylinder and not allowing the fuel-air mixture coming in to combust. Next, we have the camshaft, and that's right on top of those valves right there. And the camshaft, not to be confused with the crankshaft, is it's a long piece of metal, and it has cams on it, and cams are just really funny shaped pieces of metal that aren't quite circular or oval shaped, and they control the timing of the intake and exhaust valves. And that's very important because those valves have to open and close at the exact right time in order to not waste any fuel air mixture and not to, make your engine explode. So the camshaft is definitely very important because timing is key for all of this. Next, we have cooling methods. You may notice on this diagram it says that there's some water for cooling, which seems to be the green area along the outside of the diagram. So some of the ways that an engine can be cooled are water, but you can also use fins, which I will show a picture of later in the presentation. And that's basically just like flat little pancakes, like really thin pancakes, extending off the side of the cylinder. And how those work is they increase the surface area of the cylinder, which allows more air to get in there and carry the heat away. Water is also effective because water has a surprisingly high heat capacity, which means it can absorb a lot of heat energy without getting very hot. So it can take a lot of that energy from the metal and store it and hold on to it. And finally, another important aspect of the engine is lubrication. Lubrication is done using oil, and a lot of times that's just as simple as having a pool of oil sitting right in the bottom next to that crankshaft there, that black empty space. Sometimes you'll just have oil just pooling there, splashing up onto the moving parts to make sure everything's running smoothly and not exploding. All right, that's it for that slide. So the most important thing I want you to take away from this lesson today is the 4 strokes. Now these strokes are intake, compression, power, and exhaust in that order. And this is just a never-ending cycle, well, until you turn off the engine. It's a cycle that goes around and around, and the part of the cycle that powers the rest of the cycle is the power stroke, and the energy generated by the power stroke carries the piston around the other 3 strokes using momentum. So we're going to get into a lot of detail on these strokes on the next slide. So the first stroke is intake. So every time you think about a stroke, I want you to think about a few things. First of all, which valves are open and which valves are closed. Second of all, which way is the piston moving? Those are basically the 2 most important things that you need to think about when you're determining which stroke is which and what they do. So in the intake phase, the intake valve is open because we're trying to let the fuel air mixture enter the cylinder to get ready to burn it. So the intake valve is open to let that in, and the exhaust valve is closed because we don't want to waste that fuel air mixture. We haven't used it yet, and if the exhaust valve was open, it would just come in one valve, out the other, and you'd be spitting perfectly good fuel out of your exhaust pipe, which is wasteful and not very effective at all. So whenever the intake valve is open, the exhaust valve is always going to be closed, which is another reason why the camshaft is so important, is to control that timing. So the intake valve in the intake phase is open. The exhaust valve is closed, and the piston is moving downwards. Now, you might not understand how is the piston moving downwards, like what forces are acting on it to make it do that, and I will explain that later because, like I said, this is a cycle, and we have to start somewhere. So the piston is moving downwards, and what this does is, as the piston moves downward, it creates a vacuum, because the space where the piston was, the space that it was occupying, is now empty space as the piston moves down, and physics does not like empty space. It does not like vacuums, so all of that fuel-air mixture rushes in through the intake valve to fill that space, and that's how you get the fuel-air mixture into the combustion chamber. Next up is compression. Now in compression, the momentum from that piston going down is just going to carry the crankshaft around and back up. So now the piston is moving up. Both the intake and exhaust valves are closed. So the fuel air mixture is trapped inside the chamber. And just like the name of this stroke suggests, it's being squeezed, it's being compressed because it's trapped. It can't escape from either of the valves, and the piston is pushing up on it, the walls are pushing in, and all of those little fuel and air molecules are getting closer and closer together. And the reason why we want to do that is because it allows it to ignite more easily, and so that the piston has somewhere to go when it explodes. If the piston is at the bottom of its cycle, when the fuel air mixture explodes, it has nowhere to go and it's not going to generate any power. This way, we have some potential energy here that once we allow that fuel air mixture to combust, the piston can be pushed downwards, which is our next stroke. So the next stroke is power, and this is where all of the energy in the engine comes from. So the intake and exhaust valves remain closed, and this is very important because the spark plug is going to create a small spark, which is going to ignite the fuel air mixture. If the intake valve, for example, was open during this time, that explosion would travel through all of your pipes and just go straight to your fuel tank and blow up your whole engine. It would be a disaster. So again, another reason why timing is incredibly important here. So the spark plug ignites the fuel air mixture, which then basically explodes or combusts. It's very controlled, very small. And as it explodes, the fuel air mixture expands. And as it expands, that puts pressure on the piston and pushes it down very forcefully, which then turns the crankshaft. And that power right there, that movement, which is incredibly fast, is what's going to carry the piston through all of the other strokes. So as that crankshaft turns, it's going to keep going in a clockwise motion, as you can see from the arrows in the diagram. And as it does that, it's going to move the piston up and down because of that linkage. So the piston is pushed downwards and it turns the crankshaft. So that crankshaft is what's going to power the entire engine, your propeller, your wheels, whatever it is. And this is the part that actually generates the power that the engine is sending to your vehicle. All right, and the final phase we have here is the exhaust valve, or the exhaust stroke. The exhaust valve is open now, and the intake valve is closed because we don't want exhaust going back up into our carburetor and into our fuel tank because, well, you just have a bunch of carbon building up on the sides of your engine, and that's not very good. That can cause all kinds of problems. The exhaust valve is now open, which allows the burnt fuel air mixture or exhaust to escape the cylinder and go through the whole exhaust system. Sometimes there are additional add-ons you can have on your engine that will actually use that exhaust to give you more power, but it can just go straight out the pipe there because it's pretty much useless at this point. You just have a bunch of smoke, essentially. And the piston is moving up. It's being carried around by its momentum from the power stroke, like I said on the last slide. And because it's moving up, it is pushing all of that exhaust out of the valve to make sure that it all gets out. We're not just waiting for the exhaust particles to float up out of the exhaust valve. We're forcibly pushing them up using the momentum from the last stroke. All right, so that's about it for the 4 strokes of an engine. Those are very important, and that's basically how engines generate power. But there are a few other things that you can do to kind of customize your engine and different shapes that you can arrange these cylinders in, because engines are not just one cylinder. You would not generate very much energy at all that way. There are generally many cylinders that can be arranged in 3 main shapes that I'm going to discuss today, and those are horizontally opposed, radial, and inline. So the first engine we're going to talk about is the horizontally opposed engine. This is also called the flat or boxer engine. You might see it called that. It's the most common engine used in small aircraft today. So if you fly something like a Cessna during your O rides, if I remember correctly, a Cessna has a horizontally opposed engine. And essentially what it is you have two banks of cylinders that are directly opposite each other, like this. So the cylinders are pointing at each other, kind of canceling each other out in the same flat plane. The crankshaft is in the middle, so the crankshaft would be in between my fingers in this little demonstration, and then the pistons push outwards like this. So you can see here, yep, he's pointing. You can see the crankshaft right in the middle there, that little circular thing, and the pistons push outwards towards you see the little red caps on the end there. That's the direction where the pistons push. And I would find a GIF, but I couldn't get it to work with my presentation, so I just got a picture. These engines are usually air-cooled, and they have an even number of cylinders because each cylinder on the left side is kind of canceled out by a cylinder on the right side, so you don't have it pushing more in one direction than the other. So you're always going to have an even number of cylinders. So this engine probably has the most advantages out of any of the engines I'm going to talk about today. This is because it has a small frontal area, and this is incredibly important because everything with aircraft has to do with drag. You're always trying to reduce your drag, and this is something I talked about in one of my previous lessons, but just to recap, drag is the force that pulls your aircraft backwards. When your aircraft hits the air, it creates a force on the air, and because of Newton's laws, the air creates a force back, which pulls your aircraft back in the opposite direction of where you're trying to go. And the more area you have on the front of your aircraft that's making contact with that air, the stronger that force of drag is going to be, and your engine plays a big part in that. So because this engine has a very small front profile, if you looked at this from the front, it would seem very small. It has a lot less drag. It also has a high power to weight ratio, which means that compared to how much power it generates, it's very light and it's very smooth running. So this engine isn't only used in aircraft, it's also used in motorcycles, cars, pretty much any car that you can get is going to have a horizontally opposed engine, and helicopters. And when it's used in helicopters, essentially they just mount it sideways so that the crankshaft is pointing upwards to turn that propeller. So the next engine is the radial engine, and this engine is mostly found in older aircraft. If you look at aircraft from around like the World War II era, some of those bright yellow numbers, you'll see a radial engine, and it basically just looks like a big circle from the front. And what these are is where the cylinders are arranged in a kind of star shape, like you can see in the diagram. There's 5 cylinders all pointing outwards in a kind of star shape. The crankshaft is in the middle once again, and the pistons still push outwards. These are also usually air-cooled, and this is where I said I was going to talk about the fins on the side of the cylinders. If you look at those cylinders, you can see the fins on the side. It looks kind of jagged on the side of the cylinders, and that's exactly what I was saying. With the air-cooled cylinders, that allows the surface area to increase so that the heat can radiate off of that surface area more effectively. With these engines, there's always going to be an odd number of cylinders, and this is because the firing order of these cylinders is alternate. Not all of these cylinders are going out at the same time. It's not like out, in, out, in. It's more like out, 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 out. You know, they're taking turns. And the way that these work is alternate. So if we call the cylinder the top, cylinder 1, and the one just to the left of it, cylinder 5, then the way that this is actually going to go is we're going to go 1, 3, 5, 2, 4. So it's going around, but it's not hitting each cylinder, it's hitting every other cylinder, and because there's an odd number of cylinders, it is eventually going to hit all of them. If we had an even number of cylinders, half of the cylinders would be completely ignored during this firing order because we'd end on the same number that we started with. So there is a practical limitation of 9 cylinders just per row, just because after that it just gets too big. But you can add multiple rows. So if you just imagine that as like a cookie and you stack multiple cookies next to each other because it's kind of round, right? You just stack them next to each other and connect them all with the same crankshaft. That's how you can get more than 9 cylinders in these engines. So the main issue with these engines, unfortunately, is that they have a large frontal area, which is exactly what I was saying with the drag. Because it has a large frontal area, there's a lot more force being put on the air. There's a lot more impact going on here. And because of that, the air is going to push back harder, and it's going to negate a lot of the effects, like the thrust that's actually being generated by your engine, which is pretty bad. Another main issue with this is that because it's so big and round on the top, it reduces your visibility from the cockpit. I've actually had the pleasure of flying in a restored World War II aircraft, and I can tell you it's very, very hard to see from the cockpit of one of these because it's just sticking up so much that you can only see really the top, like the top sliver of what you would normally see like in a Cessna. If you imagine like 3/4 of your windscreen was just hidden by your engine. That's exactly what it's like to fly in one of these aircraft. So it's very difficult to see properly when you have one of these engines. It does have a higher power to weight ratio and better cooling than a lot of other engines that were available at the time. So at the time, horizontally opposed engines weren't widely available, and this is really the best that they had. It was better than a lot of the other options present at the time, and that's why it was so popular. But now that we do have the horizontally opposed engines, these are pretty much obsolete. And the biggest main advantage of the radial engine that even the horizontally opposed engine cannot beat is that it's incredibly easy to maintain. All of your cylinders are laid out very nicely. Half the time you don't even have to open up the thing to really get at it because all the air just comes in the front anyway. It's practically exposed. So you don't have to take apart very much in order to repair it and fix anything that might be wrong with it. Whereas with a horizontally opposed engine or an inline engine like we'll see later, everything is very clustered together and closed in. So if you want to fix one small part that's gone wrong right in the middle, you're going to have to take apart the entire engine just to get to it. Finally, we have the inline engine. As you can see, the picture is actually a model. There's a little coin sitting next to it, so you can see for size, but it seems to be fairly simply laid out so you can see everything properly. This is also mostly found in vintage aircraft, and here the cylinders are arranged side by side in a row along the crankshaft. So if you imagine it's like a horizontally opposed engine, but only one side, not the other side, and they're just pointing straight up. So the crankshaft is right there at the bottom, and the cylinders are pushing upwards. There's a practical limitation of 6 cylinders, and this is because when you have more than 6 cylinders in a row, the more cylinders you add, the longer your crankshaft has to be to accommodate all of the cylinders, like to reach them. And when you have more than 6 cylinders, your crankshaft actually gets so long that it's very difficult to make it out of a material and to manufacture it in a way that it's going to resist vibration while also remaining like rigid. Because the longer you make something, the more leverage all those vibrations on either end have, and they're going to make it snap. So that's why you can only really put 6 cylinders in a row in an inline engine. However, you can use multiple banks, which is where you get a V-type, H-type, or X-type engine. So basically you just put more of these together on the same crankshaft without making it any longer. This also has the same advantage as a horizontally opposed engine, which is that it has a small frontal area and less drag. It can also be installed upside down for a better visibility. You have to change the lubrication a little bit because otherwise the oil would just like pour into your combustion chamber, which wouldn't be that great. You have to move to, I believe, a dry sump lubrication. But other than that, it does provide better visibility, which is always a plus. Newer inline engines, which are being used in more high-end cars for lower operating costs and improved performance, so we might be seeing a bit of a comeback from the inline engine in general aviation. And that is it for my engine presentation. Like I said, it was fairly short, but I hope you guys learned something. If you have any questions, just let me know. And I believe Lieutenant Roberts had a model, the four-stroke engine piece to show you guys.
Oh, yes. So, so if you're part of Greenville Squadron, let me see, I'll make myself bigger here. You will get to play with this. And so, let's see if I can get this closer. This is a model of a four-stroke engine. It's probably too small on your screen to see the actual camshaft and the pistons going up and down. But it does model the full 4 strokes. Thought this was pretty neat. So you'll get to play with that when we get back into Greenville. Well, listen, that was fantastic. Really great lesson. Appreciate it. I did want to let folks know that engines is part of Chapter 1 of Module 2 for Aerospace Dimensions. So we'll actually be piggybacking off of this conversation for our next Aerospace Dimensions module, which is going to go up online, not this Friday, but next Friday. So what I'm going to do is I'm going to swing over and look at the YouTube channel. And let's see if we have any questions. Again, if you have any questions, go ahead and post them here. It usually takes about 15 seconds from the time you post the question. Well, if you post a question, I'll see it really fast, but it'll take about 15 seconds before you'll see us respond to it. Now, Iris, I don't think that Iris can see the questions. So as the questions come in, I will throw them up. Iris, you're getting a lot of good job comments. I want to echo that. Really fantastic job.
Thank you guys.
Yep, really fantastic. I think they're right now they're all voting to fire me and hire you full time. So so we're gonna send all the camera equipment and lights over to Iris's house because I agree with you guys. Did a great job. Let's see here. Any questions? So far, again, still seeing great presentations. Lots of thank yous. Okay, we'll give it about another 10 or 15 seconds. I'm actually super happy this worked, Iris. I was looking and we didn't drop a single frame. So my poor internet seemed to last after all. So
yeah, just hang in there.
Just hanged in there a little bit. So
we're testing it a little bit, but it's doing a good job.
Yep. Now, one of the folks that's watching online with us tonight is Burke Hansen. So Burke Hansen is our other Cadet AEO for Greenville. And Burke's going to be taking a shot at this as long as we can get the technology to work with Burke. He'll be taking on this in May. So Burke, you've got, I can't wait to see what you're going to talk about. And so with that, I'm not seeing any questions. I'm just seeing a lot of, hey, great jobs. So we are going to wrap this up. And so Iris, thank you so much. Great presentation tonight. And I appreciate you you joining us live. And tell your family I said hi, and hope you guys stay safe and wash those hands and all that fun stuff.
Yeah.
So,
Thank you very much for having me. I'll absolutely let them know. And everybody have a great night.
Okay. Bye, everyone. Have a great night.